All right, I think we have everybody now. So today we are going to look at parent graphs, and then we're going to focus down on some absolute value graphs. So first thing, we want to recall some standard parent functions. So we have our constant function, which is either a horizontal or a vertical line. We have our linear parent function, which is just a line that can have different y-intercepts, different slopes. You learned all about those in Algebra 1. Absolute value graphs are going to be important for us today. They look like this, a V-shaped graph. Quadratic, you focused in on Algebra 2, your parabolas. Cubic functions, x to the third power, have that little swiggle in the middle, and then there's square root graphs that look like that last one. So we can take all of these parent functions and translate them or shift them in different directions. So a vertical translation or a vertical shift moves the parent function up or down. In order to do that, we add or subtract a number to the function. So always when we do this, the number is going to be like, whoops, hanging out at the end. So I would say this +3 is hanging out at the end of the function, and so is the -5. So the +3 would shift the parent function x up by 3. And we're just talking 3 units on a number line. The second one is a parabola x squared, so it's a quadratic. The -5 out at the end would shift that parent function down by 5. And then our translation could also be called a vertical shift up. The translation down could be called a vertical shift down. So up and down movements are vertical movements. Shifts and translations are kind of used interchangeably. So anytime you have a parent function with a number out at the end, it's going to be a vertical shift moving up or down. However, here, a horizontal translation is where we have something being added or subtracted to the variable. So you'll notice in this first example here, the -2 is inside the parentheses with the variable. So that is with the variable. That actually moves the parent function to the right by 2. So if it's inside with the variable, it actually does the opposite of what the sign would appear to do. So -2 in with the variable is going to move right 2. The cube root of x would be the parent function for the next equation. The +4 is inside with the x, so it's underneath the cube root, so it's inside with the x, so that means it's going to be moving to the left by, not by 2, by 4. So +4 inside with the variable actually moves to the left by 4. And both of these shifts are horizontal shifts. So horizontal shift left and a horizontal shift to the right. Next thing we have our reflections. So for reflections, all we need is a negative sign being added somewhere to have a reflection occur. So the first reflection is the entire equation has a negative. I always say that this is out front. So it's going to be like y equals and then negative something, something, something. That's going to reflect your graph over the x-axis. So if we look at this photo here, we have the parent function y equals x squared in blue. Underneath it, they've added this minus sign right here out in front of the x squared. It's right after equal sign, there's that minus sign. That reflects the entire parent function over the x-axis. So the whole thing just gets like you're folding your paper in half and it gets put on the underside of the x-axis now. If the negative sign is in with the x, that's going to reflect over your y-axis. So this is with the x. So a lot of times it's underneath the square root. It's underneath the cube root. It is in parentheses before the cubed or in parentheses before the squared, in with that x. So here's an example. This is e to the x power. The original in this case is in red. The reflection is shown here in blue. So it's reflected over the y-axis this time. So it's like we folded our paper in half and converted it to that blue. But you'll notice, I don't know why this is so blurry, but this is f of x equals e to the negative x power. So that negative is up with the x. So that's a reflection over our y-axis. And then in this picture here, we can actually see the original, the square root of x. That's our original parent function in blue. To get our reflection over the x-axis, the negative sign here has been added to the function. So it's been added out front right after that equal sign. That has reflected it over our x-axis. And then for our graph that's in red, we have that negative being put inside the radical with the x, and that's what reflects over the y-axis. So there's our three reflection, or our parent function, and then our two reflections that could occur. So next thing we're going to do, we're going to look at some equations, and then we're going to identify the parent function, and then we're going to list the transformations that have occurred. So if I look at this first equation, I have g of x equals x squared minus 6. If I take all the addition subtraction away, I'm left with the parent function in this case, which is x squared. So that's a quadratic. The transformations are the other numbers. So in this case, the minus 6 is our transformation. We have to decide if that minus 6 is in with the variable or if it's out at the end to determine whether it's a horizontal or a vertical. In this case, we have a number out at the end. It's not in parentheses with the x. So since that minus 6 is out at the end, it's going to be a vertical shift, and we're going to move down 6. Since it's a minus 6, we're moving down 6. For question number 2, we have f of x equals the absolute value of x minus 1. Our parent function is the absolute value of x. This time the minus 1 is inside the absolute value bar, so that's going to tell me it's a horizontal shift. Since it's a minus 1, it's going to move right 1. Again, anytime a number is in with the variable, it actually goes the opposite direction of the sign. Take a minute and see if you can do question number 3. So h of x equals the square root of x plus 4. So in this case, our parent function is the square root of x. And in this case, the square root ends right here after x, so that 4 is not included with the square root, so it's not inside with the variable, so it is going to actually be a vertical shift up 4. So that plus 4 would move the parent function, the square root of x, up by 4 units. Now we're going to make it a little bit harder. We're going to have 2 transformations for these. So I have a vertical and a horizontal shift in all of these. So I'm going to start out with my parent function. If I take out the 2 shifts, this is a shift and this is a shift, that's going to leave me with my parent function x squared. So it's quadratic. And then my 2 transformations. So I have a transformation on the inside. Remember, inside moves us left or moves us right. The one out at the end moves us up or moves us down. So inside is opposite. So the plus 1 is going to move us left 1. The plus 3 out at the end is going to move up 3. Take a minute and see if you can do the next 2. All right, so for question number 6, our parent function is the absolute value of x. Our transformations, we are moving left 5 and down 2. So the 5 is on the inside of the absolute value bars with the x. That's what tells me left or right. And then the -2 is out at the end. So there's my vertical shift down 2. Question number 7. Our parent function is the square root of x. Our transformations, we are again moving left, this time by 2, and then down 5. Changing it up a little bit, we're going to be given the parent function and the transformations, and we are going to write the equation of this transformed function. So question 10, we're going to start out with an absolute value. So that's going to look like this. A vertical shift down 5. That vertical shift is going to go out at the end as a -5. And then my horizontal shift right by 3 goes the opposite. So it's going to be -3, and that's going to be with the x. So absolute value of x -3 and then -5 out at the end. Question 11, we want linear function. So that's just going to be x. Up 5 is going to be a +5 out at the end. So y equals x plus 5. Question 12, we have the square root as our parent function. We're moving down 2, so that's going to be a -2 out at the end. And then a horizontal shift left 7 would be +7, and that would go with the x. It's going to be x plus 7 when I write it. So this y equals the square root of x plus 7, end our square root there, -2 out at the end. Question 13, we have a quadratic, so that's our x squared. We want this time a horizontal shift left 8. So that's going to give us x plus 8. That has to go inside parentheses before the squared. So since it has to go inside with to get that horizontal shift, it's got to be put into parentheses. The last one here, we want a quadratic. So we're going to have x squared again. And then they tell us that the vertex is at -5, -2. If you remember from algebra 2, our vertex of a quadratic equation was always at 0, 0 unless there was a transformation made. In this case, the vertex being at -5, -2 tells me this has been moved left 5, and this tells me it's been moved down 2. So my transformations here are going to be left 5 and down 2. So our final equation for that would be y equals, in parentheses, x plus 5 squared, and then the -2 out at the end to go down 2. So next up, we're going to start some graphing. So here we're given the parent graph, the absolute value. And then we need to graph the new function according to the shifts we are given. In this case, all we have is this one shift out at the end. That means our parent function needs to be moved up by 2. So I'm going to take each ordered pair on this graph, and I'm going to move it up 2. So I'm going to start here. I'm going to go up 1, up 2. There's my new point. I'm going to take this point here. I'm going to move it up 1. Whoops, I don't know what just happened. Up 1, up 2. It's going to be right there. And I'm going to continue doing that with all these points. So there's a third one. So another one here and another one. And then I'm just going to connect those. And right there in blue is my new graph, according to the shift up 2. So that's a best case scenario. They're just one shift. There are no stretches or compressions. We don't have a lot of time to get into all of that. So anytime you're given a graph like this, hint, there might be one on the final like this, and you can identify a transformation being made. In this case, I see a transformation right here with the +4. I know that I can make a table of values, and my new center is going to be wherever that leads me. So that +4 on the inside, whoops, moves us to the left 4. That tells me that this point is going to be moved to the left by 4. Right there. However, we have this other information out here that we haven't done anything with. So when this happens, it's best to make a table of values. So we're going to make an XY table. And I'm going to start at -4. So remember, the parent function, the absolute value of X, is symmetric on both sides. So if I find half of this graph, I can reflect it to get the other half. So you can either go -5, -6, -7 and continue to the left, or you can work to the right. It doesn't really matter which way you go. So -3, -2. I would skip and let's see, go to 0. And then let's see what happens if I go all the way to the edge of the graph. So there's not a standard, you need to fill in these specific numbers for these, but when in doubt, you can plug in any X value that's on your graph to get a point. Unfortunately for these, we can't really type them in our calculators. We just have to compute them on our own. So if I look back at this original, I have -0.5 times the absolute value of -4 + 4 that I need to compute. So in the absolute value bars, -4 + 4 is 0. 0 times -1/2 is 0. So I have that point correct, -4, 0 already. Then we're just going to repeat this process for -3, -2, 0, and then 10. So -0.5 times -3 + 4. Oops. And then again, making sure you use your order of operations, you must simplify inside your absolute value bars first. So -3 plus 4 is 1. The absolute value of 1 is 1. 1 times -1/2 is -1/2. So that gives us the ordered pair -3, -1/2, which is right there. -2 plus 4 is 2. The absolute value of 2 is 2. 2 times -1/2 is -1. That's going to give me that point right there. If I plug in 0, 0 plus 4 is 4. The absolute value of 4 is 4. 4 times -1/2 is -2. If we go ahead and see what happens all the way to the right of this graph when I plug in 10, 10 plus 4 is 14. The absolute value of 14 is 14. 14 times -0.5 or -1/2 is -7. So that's going to give us a point all the way over on the right-hand side of the graph. This guy. So then if I'm careful, I can connect these the best I can. Hopefully you can do better because I'm using a stylus on my iPad. And then we want to reflect all of these points to get the other points on the left-hand side. So I'm going to have a point here, a point here, a point here. And again, we could always plug in more numbers into the original to get the rest of our graph. And that's my final graph right there. I don't think I said it earlier, but this negative out front here, since it's in front of the function, reflects over the x-axis. That's why it's been flipped down over that x-axis. We're going to practice one more. So we have, again, our parent function, the absolute value of x shown in blue. We're going to graph our new function according to the shapes we have here. So we have a reflection over the x-axis again. The -6 on the inside is going to move to the right 6. The +2 out at the end is going to move us up 2. So I know that I'm being reflected over the x-axis. The -6 is going to move us right 6, the +2 is going to move us up 2. So automatically knowing all of that, I'm going to take this original point here, 0, and I know that it needs to move to the right 6 and up 2. Right there. And again, remember, we only need to find one side of our absolute value graph, and then we can just transfer it over to the other side using the reflection property of absolute value functions. So I'm going to make myself a table. We have the ordered pair 6, 2. If you need to check it, want to check it, you can by all means plug in 6 into the original to make sure you get 2. So 6 minus 6 is 0. The absolute value of 0 is 0. -1 times 0 is still 0. And then 0 plus 2 is 2. So the ordered pair 6, 2 stands right there. Then we're going to pick numbers in order to find some more parts of our graph. I would use 5, 4, 3. Let's go all the way to 0 and see what we can get there. So that's going to give us 4 points on the left-hand side. We'll see how that looks. We might need to do some more. But we'll see. So we have -1 times the absolute value of 5 minus 6 plus 2. Absolute value comes first. 5 minus 6 is -1. The absolute value of -1 is +1. +1 times the -1 that's sitting right out front here is -1. -1 plus 2 is 1. So the ordered pair 5, 1. Right there. So I went ahead and just filled out the rest of my table, and then we're just going to compute all of those values. So 4 minus 6 is -2. The absolute value of -2 is +2. +2 times -1 out front is -2. -2 plus 2 is 0. 3 minus 6 is -3. The absolute value of -3 is +3. +3 times the -1 is -3. -3 plus 2 is -1. If I plug in 0, 0 minus 6 is -6. The absolute value of -6 is +6. +6 times -1 is -6. -6 plus 2 is -4. So if I go ahead and graph these because I got distracted. End up with these points here. And then again, that's half of our graph, so we want to reflect those points. Remember, they're being reflected over this imaginary line here. So we're not reflecting them over the y-axis. We're reflecting over this line that cuts through. So now I'm going to reflect points across. So I'm going to have a point here, here, here. And here. Then I'm just going to connect to the right. And that right there will be my final graph.